Hello, so let us now start our discussion about Boolean algebra, and specifically we will talk about expressions, functions and duality here. So let's start as usual with the definition. What is a Boolean variable? A Boolean variable is a variable which takes values in the set B, which is comprising of only zeros and 1. Okay, so a Boolean variable can either be 0 or can be 1. Okay, a Boolean function of degree n is a function from Bn to B, where Bn is given by an n tuple here. So this is an n tuple, which means that it has uh, a length of n, and each n variables, and each variable can take value from 0, 1. So all xi's belong to B, and this n tuple then will belong to B to the n. Okay. Then we have three main Boolean operators. We have a plus operator, which is similar to the OR logical operator, and it's a binary operator. Binary means that it needs two operands to operate on. Similarly there is a dot operator, which is similar to the AND operator, and it's a binary operator. It needs two operands, and sometimes this dot is removed, and it will be clear from the context. So we don't write x dot y, we just write xy. Okay, so and then we have a complement operator, which is similar to the not operator, and it's a unary operator, which means it operates on only one variable. So it's the complement of x is denoted by x bar here. Okay, a Boolean expression in variables x1 to xn are recursively defined as follows. So first of all, 0, 1, x1, x2 up to xn are expressions. And then if any of these is expression, then any of those complement is an expression, and sum of them is an expression, and the product of them is an expression. Okay. So for example, x1, x2 plus x5 is an expression. Why? Because x1, x2 is an expression because of this, and x1, x2 plus x5 is an expression because of this. Okay. Okay. So this is a basic explanation of some definitions. Now we talk about duality. So what does duality mean? So if f is a Boolean function, then its dual, which is denoted by f to the d, is formed by the same variables, but by interchanging plus with dot, dot with plus, or plus with product, product with addition. 0 is replaced by 1, and 1 is replaced by 0. So for example, if I have, let's say, x1 times x2 plus x3 plus 1. So what is the dual of this? So the dual of this is x1 remains x1. This is multiplication, right? So I'll say plus in brackets. Then these are additions. So x2 dot x3 dot, and 1 is replaced by 0. So we have 0. So this is the dual of this guy. Then x1, x2, x3 will not change. The product is replaced by the sum is replaced by the product, and 1 is replaced by 0. Okay. So duals do not depend on the expressions representation. So for example, if let's say if we have x plus y times z, so this is also equal to x plus y times x plus z. This is a property we will study later. So this expression is equivalent to this expression. So the dual of this expression, it will be the same as the dual of this expression. So this means that it does not depend on which representation we are using. Okay. Okay. In other words, if these expressions are equivalent, then their duals are also equivalent. Okay. Okay. Then we show a brief summary of Boolean identities. Now these identities are used, I mean, you can find them in any textbook. But I like to write them because when we do the examples, I would like to refer to them so that it will be more clear. Okay, so uh, we don't need to go through this, line by line, but you can have it as a reference here. Okay, so now let's jump into some problems here. So my first problem is like this: how many functions of degree n are possible? Okay, so these are two problems, but let's say how many functions of degree n are possible. Now function of degree n, what is what? As a mapping from, or a function from b to the n to b. Okay, so this means my input has n uh, spaces or n positions. Okay, and my output or my function value, this has only one position. Okay, so n positions and one position. Okay, now if we have n positions, how many total inputs can I have? I can have 2 to the n total, I should not say total, 2 to the n different inputs, correct? So for each of these 2 to the n inputs, my output can be either 0 or 1. Okay, so then this means that, so let me write one more sentence. So output is 0 or 1 for each of these 2 to the n inputs. Okay, so for how many options we have? We have two options for each of these 2 to the n inputs. So this means then we can have 2 to the n functions of degree n possible. Let's take an example here. Let's say we have n is equal to 2. Okay, so my inputs can be either 0 0 0 1 1 0 and 1 1. So I have 4 inputs, correct? So this means what? Let's say I call this as A, this as B, this as C, and this as D. So for input of A, I can have either 0 or 1. I can have either 0 or 1. I can have either 0 or 1, and I can have either 0 or 1. So how many combinations can I have? I can have 0 0 0 0, I can have 0 0 1 1, I can have 1 1 1 1, 1 0 1 1, and so on. So I have, how many combinations I have? 2 to the 4 combinations I can have for my function. So this means there are 16 possible functions of degree 2 possible. Okay, but now let's say how many, if there's some condition is applied. So let's say that I have three variables. I have n is equal to 3 and my variables are x, y, and z, and my function is f. Now I'm told that f of x, y, z, this is equal to f of x bar, y bar, and z bar. Okay, now note that since I have three inputs, then I have total 3 bits, then I have total of 8 possible input combinations. But I am also told that f of x, y, z is equal to f of x bar, y bar, z bar. So this means for whatever the value I choose for 0 0 0, if I choose 0 here, for 1 1 1 I have to choose 0 here, because 1 1 1 is x inverted, x complemented, y complemented, and z complemented. Similarly, if I choose 0 0 1, then 1 1 0. So this means 0 or 1. So this are the same, and then these are the same. Similarly, you can check for 0 1 0 and 0 1 1. We can have only one of them we can choose. The other one we cannot choose. So then this means that earlier we had 2 to the 8 of them. but now we will have 2 to the 8 over 2 of them, because we can only choose 4 of them. Okay, so then this is 2 to the 4, which is equal to 16. Okay, so this is when we impose some constraint that our function values is equal to some other function values when we change the input combination. So then obviously we cannot our overall degree of freedom will go down because we can only choose some of them. Okay, okay, so then my next question is that we want to find the relationship between duality and complement. Okay, in other words, what we want to show is that the dual of f of x, so for example x1 x2, this is equal to sum x1 bar up to xn bar and then bar. Okay, so this is what we want to show. So for this we have to make use of these two. Okay, so now let's start with this one. So starting with this one, what does it mean? That we have x1 bar, x2 bar, but we are taking the complement of the whole thing. So then this means, and when we take the complement of the whole function, whatever the function is, it can be in a form like this. So whatever the function is like this, so this one we will say that this outer complement will result in plus change to plus and dot change to dot or plus, correct? Because of this guy, because De Morgan's law say that x plus y, if I take the complement of the full thing, then I get x bar and y bar. Okay, and then if I take the complement of xy, then I can get x bar plus y bar. Okay, hope it makes sense. So then, but then we have x bars here, so this means x bar I have to complement again. So then the inner complement will make x bar to x double bar, which is equal to x because of double complement here. Okay, so then this is exactly the same definition as the dual, right? So what we do, we don't change our variables, we change our plus and dots to plus to dot and dot to plus. Okay, what about this plus 1 and minus 1? What will happen to them? Because they will be inverted, right? Because of this one, 1 will be inverted to 0 and 0 will be inverted to 1. Okay, so this means 1 and 0 to 0 and 1. Okay, so this is exactly the definition of dual of a function. Okay, so then what we did, we just used some definitions and the De Morgan's laws to prove that the dual of a function is equal to the complement of the function when that function is applied to the complement of the variables. Okay, so this can be thought of another definition of the dual function. Okay, I would say this is a good idea to remember what is dual of a function. Okay, so this is it about an introduction of Boolean algebra expressions and some definitions and some basic extensions we can make just by observing the definitions and using some basic Boolean identities. Okay, so hope it was easy to understand and thanks for watching. Hope you liked the video.